All right, let's dive in. Today we're going to explore something that's all around us, but we can't actually see it.
Hmm, sounds intriguing. I'm all ears.
We're talking about magnetic fields.
Ah, yes. Those invisible forces that are constantly at play.
And to help us visualize these invisible forces, we're going to turn to a pretty cool resource.
Oh, what is it?
It's an educational website called Open Educational Resources, Open Source Physics at Singapore.
I've heard of them. They do some really interesting work.
Yeah, and they have all these interactive physics simulations.
That's a great way to make these concepts come alive.
Right, and we're going to zero in on one that explores magnetic fields, specifically the ones generated by two wires with electrical currents flowing through them.
So we're going beyond just the basic idea of a magnetic field around a single wire.
Exactly. We're going to see how these fields interact. So the simulation, it shows these two parallel wires, right? And you can actually click around and see how the magnetic field lines change.
Oh, so it's not just a static picture. You can actually manipulate the variables.
Yeah, you can change things like the position of the wires and the amount of current flowing through them.
I bet that leads to some interesting observations.
It definitely does. You start to see that the magnetic field from one wire influences the field from the other.
Ah, so it's not as simple as just having two separate fields. They're actually interacting with each other.
That's right. And this is where things get really cool, because the direction of the current actually determines whether the fields strengthen or weaken each other.
Oh, so it's like they can either work together or against each other.
Exactly.
And the simulation lets you visualize that push and pull between the fields.
It's pretty amazing to see. So, for example, if the currents are flowing in the same direction,
What happens then?
well, the magnetic fields between the wires actually oppose each other.
Hmm. So that would create a weaker field in that region.
You got it.
Hmm.
But on the outer sides of the wires, the fields reinforce each other, creating a stronger field.
So it's this dynamic interplay between the fields, depending on the direction of the current.
And the simulation really brings that to life.
Fascinating.
But okay, let's zoom out for a second and think about why this matters in the real world. Why should we care about these interacting magnetic fields from wires?
Well, think about it. Wires carrying electric current are everywhere. They're the backbone of our entire electrical infrastructure.
That's true. From the wiring in our homes to the power grids that span entire cities.
Exactly. So understanding how these magnetic fields interact is crucial for designing efficient and safe electrical systems.
Right, because we don't want those fields interfering with each other in unpredictable ways.
And it goes beyond just power distribution. These principles are also at work in things like electromagnets.
Ah, yes, electromagnets. So we're talking about motors, speakers, those giant cranes that pick up scrap metal.
Exactly. By manipulating magnetic fields, we can create powerful forces that are essential for countless technologies. Even something like a magnetic levitation train relies on these principles.
Wow, magnetic levitation trains. So we're talking about real-world applications that could revolutionize transportation.
Absolutely. But the website doesn't just show us these fields, it also prompts us to think about them in a deeper way.
You mean those questions they pose?
Yes. Yeah. Like, how does the field change as you move from a single wire to a coil with many loops?
Interesting. So instead of just two parallel wires, we're now thinking about a wire wound into a coil.
And then they ask, what happens in the center of the coil? Why?
Oh, that's a great question. I have a feeling that exploring that will unlock even more insights into the power and complexity of magnetic fields.
And that's exactly what we'll do in part 2 of our deep dive. We'll delve deeper into solenoids, unravel those mysteries, and uncover even more real-world applications.
Awesome. Can't wait. So let's pick up where we left off. We were talking about that question about a coil with many loops.
Ah, yes. That takes us into the world of solenoids.
Solenoids, right. Now, I vaguely remember that term from physics class, but could you give us a quick refresher?
Of course. Imagine taking a wire and winding it tightly, like thread on a spool.
Okay, I'm picturing it.
That's essentially what a solenoid is. And when you pass an electric current through this coil, it creates a magnetic field. But it's not just any magnetic field. It's much stronger and more uniform than the field from a single straight wire.
So coiling the wire amplifies the magnetic field. Why is that?
Well, think about it. Each loop in the coil is creating its own little magnetic field. And inside the coil, all these individual fields point in the same direction, so they add up.
Ah, so they're all working together. The more loops, the stronger the overall field.
Exactly. And because the field lines are all aligned within the solenoid, you get a very uniform magnetic field, especially in the center of the coil.
Okay, so we've got this strong, uniform magnetic field inside a solenoid. What can we actually do with that?
Well, this principle is used in tons of technologies.
Like what?
MRI machines, for instance. They use powerful solenoids to create a uniform magnetic field that interacts with the water molecules in your body. That's how doctors can get those detailed images of your organs and tissues.
Wow, that's pretty amazing. Something as simple as a coil of wire can have such a huge impact on healthcare.
Absolutely. And solenoids are essential in a whole bunch of other devices too.
Like what?
Speakers, microphones, even the hard drives that store your computer data, they
Hmm.
all rely on the precise control of magnetic fields that you can get from solenoids.
It's incredible to think that we're surrounded by solenoids every day.
They really are everywhere.
Okay, so back to the simulation. They also asked about what happens in the center of the coil. What's so special about that spot?
Ah, yes. Well, at the center of the solenoid, the magnetic field lines are perfectly straight and parallel.
And that creates,
It creates a region of incredibly uniform magnetic field strength.
which is important for.
For many of the applications we just talked about, like for an MRI to work properly, it needs that perfectly uniform magnetic field, otherwise the images would be distorted.
So it's not just about the strength of the field, it's also about how evenly it's distributed.
Precisely. That uniformity is also crucial for accuracy in things like scientific experiments and industrial processes.
This deep dive is really opening my eyes to the hidden world of magnetic fields.
It's fascinating, isn't it?
Now I'm going to look at every coil of wire and wonder what invisible forces are at play.
That's the beauty of physics. It reveals the hidden workings of the universe.
Absolutely. But there's another layer to this that we touched on earlier, magnetic flux.
Ah, yes, magnetic flux. It's essential for understanding how magnetic fields interact with conductors.
Right, it's like a measure of the flow of the magnetic field lines.
Exactly. And here's where it gets really interesting. When you change the magnetic flux through a coil of wire, you can actually induce an electromotive force.
An electromotive force? Is that like...
It's basically a voltage. It can drive an electric current. This is known as Faraday's law of induction.
Hold on, are you saying that a changing magnetic field can create electricity?
You got it. This is the principle behind how generators work. You have a coil of wire rotating within a magnetic field. As the coil spins, the magnetic flux through it changes, inducing an electric current. And that's how we generate electricity to power our homes and cities.
Wow, that's mind-blowing. So this concept of magnetic flux, it's not just some abstract idea.
Yeah.
It has a direct impact on our lives.
Absolutely. It's the basis for a wide range of technologies, from generators to wireless charging and induction cooking.
Okay, now I'm really starting to see the world in a new light. Literally.
It's amazing what you discover when you start looking at the world through the lens of physics.
Speaking of discoveries, the simulation website also raises another interesting point. It asks about those arrows on each end of the wires in the diagram, one red, one blue.
Oh, yes, I see those.
And it asks, which one shows the direction of the current?
Ah, that's a great question, because it actually gets into a subtle point about how we represent electricity.
It seems pretty straightforward. Don't the arrows just point in the direction the electricity is flowing?
Well, it's a bit more nuanced than that. We have to consider the difference between conventional current and electron flow.
Okay. Now I'm intrigued.
Yeah, it's a bit of a historical quirk, really.
Okay, well, let's unravel this mystery in part 3 of our magnetic deep dive. We'll explore those conventions, dive deeper into magnetic flux, and see what other surprises these invisible forces have in store for us.
Sounds like a plan. I'm looking forward to it.
Okay, so where were we? Oh yeah, those arrows in the simulation, and which one shows the direction of the current?
Right, and like I was saying, it's not quite as simple as it might seem at first glance.
You mentioned something about conventional current versus electron flow.
Yeah, so it kind of goes back to the early days of studying electricity, right? Scientists didn't actually know which way the current was flowing.
So what do?
They basically just picked a direction and went with it. And they established a convention that current flows from the positive terminal to the negative terminal of a battery or power source.
So they just made a guess.
Well, it was an educated guess based on the observations they had at the time. But the important thing is that they created a standard, a convention. And we still use that convention today. We call it conventional current.
Okay.
But then later on, as our understanding of electricity improved, we discovered that the actual charge carriers are electrons. and electrons are negatively charged,
Right.
and they flow in the opposite direction from negative to positive.
Ah, so that's where the confusion comes in.
Exactly. So we have these two different perspectives on current flow. The conventional current, which is what's shown in a lot of diagrams and simulations, and then the actual electron flow.
So in the simulation we're looking at, those arrows represent,
They represent the direction of conventional current flow.
even though the electrons are actually flowing the other way.
Right. It's just important to keep that in mind when you're interpreting the results.
It's a good reminder that even in science, things aren't always as straightforward as they seem.
That's for sure.
Okay, but let's talk a little bit more about magnetic flux. We touched on it in the last part.
Yeah, magnetic flux. It's kind of a tricky concept, but it's really important for understanding magnetic fields.
So can we try to explain it in a way that makes sense?
Okay, let's try. Imagine you have a river,
A river. Okay.
and you're looking at a particular section of the river. The amount of water flowing through that section, that's kind of like the flux.
So more water flowing through means higher flux.
Exactly.
Yeah.
And with magnetic flux, it's the same idea, but instead of water, it's magnetic field lines. It's a measure of how many field lines are passing through a given area.
Ah, I see. And the simulation uses color to represent that, right?
Yeah.
Brighter colors mean higher flux.
Yeah, exactly. So you can kind of see how the flux changes as you move around the wires or adjust the current.
It's a really cool visualization. But magnetic flux, it's not just about pretty pictures, right? It's connected to some pretty important physical principle.
Absolutely. Remember Faraday's law that we were talking about?
Vaguely. Refresh my memory.
Faraday's law says that if you change the magnetic flux through a coil of wire, it creates an electromotive force, basically a voltage.
And that voltage can.
It can drive an electric current.
So a changing magnetic field can actually generate electricity.
That's right. And that's how generators work.
Really?
Yep. You have a coil of wire spinning inside a magnetic field. As the coil rotates, the magnetic flux through it changes, which induces a current.
Wow, that's amazing. So all those power plants we rely on, they're essentially just manipulating magnetic flux.
In a way, yes. And it's not just power plants. Think about wireless charging.
Wireless charging, how does that work?
It uses a coil to create a changing magnetic field. And when you bring your phone close to the charger, that changing magnetic field induces a current in a coil inside your phone, which charges the battery.
It's like magic, but really it's just physics.
Exactly. And induction cooktops work on a similar principle. They use changing magnetic fields to induce currents directly in the metal of your cookware, which generates heat.
Wow, it's amazing to think about all these applications of Faraday's law, from huge power plants to the appliances in our kitchens.
It really shows how these fundamental principles of physics are woven into the fabric of our everyday lives.
I think this deep dive has been a real eye-opener. We've explored the interactions between magnetic fields, the power of solenoids, the magic of Faraday's law, and the sometimes confusing conventions we use to represent these phenomena.
And hopefully we've demystified some of these concepts along the way.
Absolutely. It's so easy to take these invisible forces for granted, but they really are shaping the world around us in so many ways.
It makes you appreciate the beauty and complexity of the universe, doesn't it?
It really does. So to everyone listening, I encourage you to check out that simulation we've been talking about and all the other great resources on the Open Educational Resources Open Source Physics at Singapore website.
There's a whole world of fascinating physics to explore.
So keep exploring, keep asking questions, and keep diving deep. We'll see you next time on The Deep Dive.